We're always looking for those big shifts, the
Yeah.
kind that completely change how we see the universe.
Mm.
And in physics, well, the ultimate prize, you could say, is a theory of everything.
Right, that single idea that explains it all.
Exactly.
Yeah.
A single framework for every force, every particle. It sounds amazing,
Yeah.
but it's proven incredibly tough.
Oh, absolutely. For decades, the real sticking point has been trying to bring together Einstein's general relativity, that's gravity on the grand scale, stars, galaxies.
It's your big picture stuff.
Right. And quantum mechanics, which is, brilliant for the tiny stuff, atoms, particles.
Two theories, both incredibly successful on their own turf.
Precisely. But getting them to work together, that's been the puzzle. Generations of physicists have wrestled with it.
Okay, well, hold on, because there might be something new on the horizon.
Oh.
Yeah. Researchers over in Finland at Aalto University, Mikko Partinen and Jukka Toki,
Ah, okay.
they put forward a new quantum theory of gravity. And the early signs are, well, they suggest it could be a really big step.
Towards bridging that gap you mentioned.
That's the idea. This is that kind of fundamental research that really pushes boundaries.
It is. So in this deep dive, we really want to get into the nuts and bolts of this new theory.
What's the core idea? What could it actually mean for how we understand things?
And we should stress it's still early days for this research, but the potential implications, they're huge.
Definitely. And for anyone listening, maybe preparing for exams like the UPSC, getting your head around these fundamental debates in physics, it's really valuable context.
It helps see the bigger picture of scientific progress.
And, it's worth remembering this really abstract-sounding physics. It can have surprisingly real-world effects down the line.
Like Einstein's relativity.
Exactly. We literally use it every day with GPS. It's not just theory. It's in our phones, our cars.
That's a great point. Fundamental understanding can lead to unexpected tech.
Okay, so let's dive in. What's the basic problem Partinen and Toki are trying to solve here? What's this incompatibility?
Well, fundamentally, it's how the two theories treat gravity. General relativity sees gravity as like the shape of space-time itself.
Yeah.
Mass and energy curve this space-time fabric, and that's what we feel as gravity. It's smooth, continuous.
Like a trampoline bending under a bowling ball?
Sort of, yeah. But quantum field theory describes the other forces, electromagnetism, the nuclear forces, very differently.
Oh, so.
As interactions between particles mediated by force-carrying particles happening in little jumps, discrete packets, quanta. It's probabilistic, quantized.
So, smooth versus jumpy, continuous versus discrete.
That's a good way to put it. The math is different. The whole way of thinking about it is different. Trying to just smash them together hasn't worked. It's like different operating systems that just won't talk to each other.
Okay, so these two rock-solid theories just can't agree on gravity.
Yeah.
Now, this new Finnish approach, what makes it different? What's the innovation?
What's really interesting, I think, is they aren't trying to do what others have tried, like directly quantize space-time itself. That's been the main path, and it's hit dead ends. Instead, they're trying to frame gravity using something called a gauge theory.
Gauge theory. Okay, unpack that a bit. What does that mean here?
Sure. Think about, say, the electromagnetic force.
Yeah.
You have charged particles like electrons. They interact by swapping photons, right? The force carriers, that whole interaction. It's described perfectly by a gauge theory.
Okay.
And a key idea in gauge theories is symmetry. Certain things can change locally, but the underlying laws stay the same. It's a very powerful mathematical framework.
So Partinen and Toki are applying this gauge theory idea to gravity.
Exactly. They're proposing that particles with energy interact via the gravitational field, much like charged particles interact via the electromagnetic field.
Ah, so it's an interaction through a field mediated perhaps by particles rather than just the bending of space-time itself.
That's the core shift in perspective. They're looking for symmetries in gravity that look like the symmetries we already know work for the other forces in the standard model.
The standard model. That's our current best theory for everything except gravity, right?
Precisely. It describes the electromagnetic, weak, and strong nuclear forces using gauge theories. So they're trying to bring gravity into that successful family, so to speak.
Instead of seeing gravity as just the stage space-time, they're seeing it as another interaction happening on the stage.
That's a really good analogy. General relativity focuses on the geometry of space-time. This new approach focuses on gravity as an interaction between things that have energy, using a framework similar to other forces.
Okay, this is where it gets really exciting. If this pans out, if this gauge theory for gravity actually works,
Yeah.
what kind of big questions could it help answer?
Oh, the potential is immense. Think about singularities.
Inside black holes.
And the Big Bang itself?
Exactly. Our current theories, general relativity and quantum mechanics, break down there. They predict infinities, which basically means the theory has stopped making sense.
Physics just throws its hands up. Pretty much. But Parton actually said, if this turns out to lead to a complete quantum field theory of gravity, then eventually it will give answers to the very difficult problems of understanding singularities and black holes and the Big Bang.
Wow. Actually understanding the birth of the universe, the heart of a black hole. That's profound.
It really is.
What about that term theory of everything? I noticed the researchers seem a bit cautious about using it.
And rightly so. It's scientifically careful. While a theory that unites all the forces is often called that, they know there are other deep mysteries out there.
Like,
Why is there so much more matter than antimatter in the universe? A true, complete theory of everything would ideally explain that too.
I see. So this is maybe a massive piece of the puzzle, but perhaps not the final complete picture just yet.
That's a fair way to see it, a potentially crucial step forward.
Right. Now, any new theory, especially one this ambitious, faces huge hurdles. What are the big challenges for Portman and Tolkien right now? What do they need to prove?
Well, a really critical thing in these kinds of theories, quantum field theories, is dealing with infinities that pop up in the calculations.
The ones that signal the theory is breaking down.
Not quite breaking down, but infinities that appear in intermediate steps of the math that shouldn't be in the final physical answer. There's a set of mathematical tools called renormalization to handle them.
Okay, so you need to show your theory can be renormalized.
Exactly. You need to show you can consistently get rid of these infinities and get sensible, finite predictions. Now, Partonen and Kalki have shown this works for what we call first-order calculations.
Like the first simplest approximation.
That's right. But you need to show it works consistently as you add more complexity, more precision, what we call higher-order terms.
And if it doesn't?
Then you're back to getting infinite nonsensical results. As Tolkien put it, if renormalization doesn't work for higher-order terms, you'll get infinite results. So it's vital to show that this renormalization continues to work.
So the foundation seems solid, but they need to prove the whole building is stable as they build it higher, essentially.
That's a perfect analogy, but they seem optimistic. Partonen mentioned they expect to know much more in the next few years. The progress so far is definitely encouraging.
And it's great they published in reports on progress in physics. That feels like a clear invitation to the whole community, doesn't it?
Oh, absolutely. That's how science should work. Put your ideas out there, let others test them, critique them, build on them.
Peer review and collaboration.
It's essential. Science is a team sport, really, even if the players are all over the world.
When you think about the history of physics, breakthroughs like this, if confirmed, could be genuine paradigm shifts, couldn't they?
Without a doubt. Partonen himself made that connection. He said, like quantum mechanics and the theory of relativity before it, we hope our theory will open countless avenues for scientists to explore.
Those theories didn't just change physics, they changed everything, leading to technologies nobody could have imagined.
Exactly. A fundamental shift in understanding gravity at the quantum level. Who knows where that could lead? It could spark a whole new era of discovery.
It really is exciting to think about.
Yeah.
Okay, so let's try and summarize. What's the key takeaway from all this?
The main thing is this. We have a new, potentially viable way to think about quantum gravity coming out of Finland. It uses the successful framework of gauge theories.
Like the other forces.
Right. And it offers a path, maybe, to finally unify gravity with quantum mechanics and tackle huge mysteries like singularities.
But, and this is important, it's still a work in progress.
Absolutely. Rigorous proof is needed. Science demands that skepticism and thorough testing.
No question, the community will really put it through its paces.
As they should, but the initial signs are promising, and it's definitely got people talking.
It really makes you think, doesn't it? This ongoing quest to figure out the deepest rules of reality. Imagine we did get a complete theory of everything. How would that change our view of everything?
That's the big provocative thought, isn't it? What new horizons would open up. It really shows why this fundamental science is so important.
Absolutely. Well, this has been a really fascinating deep dive, exploring this potential breakthrough. And remember, all this info comes from Science Tech Daily.
A great source for staying updated.
Definitely. So if you found this interesting, you want to keep up with these kinds of developments, Do make sure you like, subscribe, and maybe drop a comment.
Yeah, let us know your thoughts or any questions you have.
We'd love to hear from you.